This video is extremely important for Calculus 3, aka multivariable calculus, because we'll be going over these notations here, including the del, the curl, and also the divergence. And this right here could be really confusing sometimes. We just really have to know these notations really well. Starting with the first one, the little f, which is just like our regular function, but now we have more than one variables because we're in multivariable calculus. Let's say we have three variables, then we will have f of x, y, z. Now have a look. When we plug in x, y, and z into the function and work it out, the result is what? A number, right? So this is an example of a scalar function, which is different than the next one. When we have r with an arrow on the top, this is going to be a vector function. R is usually for the position. You can imagine the position of a flying in a room. Right here, I will write r, and our input will be t. This is a parametric function. We have the three components, x, y, and z. And the result of this is going to be a vector. And now notice that this is called a vector function when we just have one input, namely the t. The next one, when we have a capital F with an arrow on the top, this is a vector field. The difference between this and that is that this right here, it's a vector with three components, but each component is a multivariable expression. We are going to write it as P of x, y, z, and then Q of x, y, z, and lastly, R of x, y, z. And you can imagine this right here, it's pretty crazy, right? Because we have a lot of things going on already. Yeah. Next, this upside down triangle is called the del. It's an operator and it's a factor, and you can think about it as a factor of the operators. The first one is going to be the differential operator, the partial derivative with respect to x. And the second one is the partial with respect to y. And the third one is going to be with respect to z. And in fact, there's no work to be done right here because this notation always means this only. It's just a factor of these operators. Next, when we have del with a little f, notice that when we have del, which is a factor, and little f is a scalar function, and you don't really need any indicated operation in between. You don't need a dot, you don't need a cross. This right here is defined to be the following. You look at what the function f is, and then you do the partial derivative with respect to x. That will be the first component. If you do it with respect to y, that will be the second component. Lastly, do it with respect to z, that will be the third component. And this is also called the gradient factor. Now, the next one is the curl of the vector field f. Have a look. The curl of f, this right here has to be a vector field. And the definition of this is that we will take the del, and then we do the cross product with our vector field. How can I remember this is the cross product? Well, the curl starts with a C, so it's a cross product. And now you might be wondering, this is the divergence of f, so what do we do? Yes, if you're saying the dot product, you're absolutely right. This is the del dot f. Now, this is a vector, this is a vector, we have a cross product. Likewise, a vector and vector dot product. This right here makes sense. Right here, let's just quickly review how to set up the cross product for this right here. Okay, we'll just be pretty much doing the 3x3 determinant matrix, right? The first row is going to be the unit vector I, j, k. The second row, it will be the del, which is this, and that. So partial with respect to x, partial with respect to y, partial with respect to z. And these are just the operators. Lastly, we'll put the f, pqr, in the third row. Now, here's the deal. I would recommend you guys to do the cofactor expansion when you want to find the determinant of this 3x3 matrix. The first part will be, you start with this, you delete this column and this row, and then you have to find this determinant of this 2x2 matrix. When you do this times that, what you are really doing is you take the partial derivative of r with respect to y, and then you subtract this times that, which is the partial of q with respect to z, etc. Okay, so that's pretty much it. And then for the dot product, it's this factor here dotting with this factor here. So this right here is equal to, when you do this dot dot, you just multiply, but really you are taking the partial derivative of p with respect to x. And then you are going to add partial of q with respect to y, lastly partial of r with respect to z. Now remember, the result of a cross product is a factor, but the result of a dot product is an expression. Keep that in mind. So this is pretty much it. However, I do want to mention a few more things. First is our factor field f here and also our del of f here. Are they always the same? No. And here is the deal. Right here, we say a factor field f is conservative. So this right here is the key word. And then the definition for that is, if we can find a little f such that if we do the del of little f, we get the factor field f. But this is not always equal to that. It's not always possible to find such a little f so that this happens. But if it does happen, then we say f is conservative, the factor field. And if a factor field is conservative, you actually get to use many different theorems. For example, the fundamental theorem of line integrals, and that's quite nice. However, how do we check if a factor field is conservative or not? Well, we can use the curl to help us out. So this is the first thing. And then the second thing is that if we compute the curl of our factor field f, if we get 0, but be careful, this right here is a cross product, and the result of it shall be a factor. So this right here is technically a 0 factor. So we are talking about 0, 0, 0. Just some small detail. You can almost always be sure that our capital F is conservative. However, more details coming. We have to make sure that P, Q, R are nice. How nice is nice? I'm going to write that down for you. If we have P, Q, R have continuous partial derivatives. It's not that they have a nice cars or nice houses. It's that they have continuous partial derivative. That's how they are nice. When we have all that, then we can be sure that our factor field f is conservative. And sometimes you want to check this first, because if you can be sure that our factor field is conservative, that means you can find such a little f so that this happens. Because if our factor field is not conservative, then this right here is not possible, so don't even try. So hopefully this right here is helpful. Definitely check out my other videos because I have more examples for you guys.